So this is a problem. I guarantee you, you'll have something similar on your for your homework, for the exam, and you'll have something like this. I mean, something like this on the final. So you really and in your lab. So you want to know how to do it. Okay, a billiard ball, a pool ball, moving at 5 meters per second, strikes a stationary ball, same mass. After collision, the original ball goes at this velocity at a certain angle, and the other one goes somewhere else. So we want to find the velocity and the angle of the ball that was struck. So it's a two-dimensional momentum problem. Now, you've got to make an assumption, right? I mean, it's pool, you know? And so everything's moving along the horizontal plane, and they don't give us any information about friction. So you're going to assume that the friction along the horizontal plane can be ignored. So that means that the momentum is only conserved along the horizontal plane. Okay? All right, so that's super important. The momentum is conserved only along the horizontal plane. But that's, again, that's cool because everything's going along, everything's happening along the horizontal plane. Okay, so the first thing you've got to do is draw the picture. Okay, so I guess I already have it drawn. So, okay, so we're looking down on the table. So, yeah, this is the white ball and the black ball, okay? So this is the one that's stationary, has the same mass. So this one comes along and smashes it. So this is before. Then after, the white ball goes that way, that speed, that angle. So this one is going to go some other angle with some other speed. And what we want to find is that. Okay, so we got to make a coordinate system. So it doesn't really matter, but I'm going to say this is x because I feel like it. I'm going to say that's y because I feel like it. Doesn't, all right? All right, and you know, we're going to say that this is, you know, plus y. This is plus x, okay? So plus, plus, minus, minus. And again, momentum is conserved. That's what we want to use, momentum conservation, right? Momentum conservation. 2 dimensions, right? So not a problem. So px initial equals px final. All right, so let's do it. Now, these guys have mass m, but then we're going to have like meters per second, so the m's are going to look weird because we're going to have m's all over the place. And so I'm not going to write units. Okay? No units. We're just going to make sure everything is in, you know, metric system units, okay? Otherwise, it just is a mess. It's hard to figure out what's the m as a mass and what's the m as a meter. Okay, so so what's the initial momentum? So mass times velocity. Again, no units. So the mass is m, velocity is 5. So the momentum is 5m. So 5m. What's the momentum of this guy? 0. Okay, all right, this is along the x. What's the x momentum of this guy? Well, we've got to use, you know, cosine, right? So it's going to be, the mass is m, velocity is 4.35, cos 30. So 4.35 is the speed. The mass is m. Well, let's just say 4.35 cos 30, right? That's a component of the velocity along the x direction. And we want to multiply that by the m. And then the other guy is going to be v cosine theta times m. So v cos theta times m. Now, what do you notice? If they both have the same mass, we can get rid of the masses. Isn't that nice? So divide by the masses. That's nice. All right. So what we have then is we have, I should have wrote whatever. So therefore we have 5 equals 4.35 cosine 30 plus v cosine theta. All right, there we go. Awesome. And you know what, I mean, we have 2 variables, right? We have the the velocity and the theta. So we know, you know you're going to have two equations, right? Two equations to two unknowns. Okay, Py initial equals Py final. All right, well, is there any, remember this is the y. What's the initial y momentum? 0, right? Because this is all along the x. So there's no, remember this is x, this is y, right? Along the horizontal plane. So the initial y momentum is 0, wonderful. And then this is going to be 4.35 sine 30 times m. So 4.35 sine of 30 times m. And this one, got to be careful. This is plus y, this is minus y. So this y component is down. You got to remember that minus sign. So it's minus v sine theta times m. And again, get rid of the m's. So we're going to have 4.35 sine 30, put that on the other side, equals v sine theta. Okay? Whatever. Okay. Now you can solve it however you want to solve it. Doesn't really matter. Let's rewrite this one. Let's solve for the v cos theta. You'll see why. So v cos theta equals 5 minus 4.35 cos 30. All right. So this is how I solve it. You don't have to do it this way. Just I like it. Okay. So all right. So v sine theta is what I have here. Divided by v cos theta. Divided by v cos theta. Well, gosh, what is that? The v's cancel, and you just get sine over cosine, which is tangent. Just tangent theta. Well, what's v sine? V sine is 4.35 sine 30. 4.35 sine 30. And what's v cos? V cos is this thing. 5 minus 4.35 cos 30. Well, awesome. Well, wait a second. I don't want tangent theta. I want theta, right? So theta is tan inverse of that. Okay? And I promise you do that, you get 60 degrees. All right, okay, we got the angle. Now we want the v. So, pick any equation you want to get the v. Let's use this one. So v is 4.35 sine of 30 divided by sine of theta, which is sine of 60, right? And I promise you do that. And you get 2.5 meters per second. Ta-da. Okay, so that's all you do, You just write momentum conservation in the x direction, momentum conservation in the y direction, and you just math, and then you just solve however you want to solve. That's all there is to it. Not so bad. Okay. All right, here's a question. Oh, this is a good one. Suppose rain falls vertically into an open cart rolling along a straight horizontal track with negligible friction. As a result of the accumulating water, what happens to the speed of the cart? Yeah, this is one, please do this. Analyze, don't philosophize. Use conservation of momentum. If you just go by your gut, you're probably going to get it wrong. So use conservation of momentum. So pause your video and figure it out, please. Okay. All right, so you should be looking for this. Okay, it's moving along the horizontal plane, negligible friction. So that means that momentum is conserved along the horizontal plane, right? Okay, now, so we know M initial, V initial equals M final, V final along the horizontal plane. Or actually it's just going in one, it's actually just going in, let's say, the X direction or something like that, right? Okay, so this is true, you know? But the rain, notice it's falling vertically, right? It's not going, you know, it's not going along the horizontal plane. That's kind of crucial, you know. Okay, so we know that this is true because there are no external forces, right? The rain is vertical, so it's not a horizontal force. So horizontally, it's an isolated system. So along this direction, momentum is conserved. But what's happening to the mass, though? You know, the rain is falling into the cart, right? So this has to be bigger than that, right? So therefore, if this product equals that product, this is getting slower. You know, this is whatever, right? This is some speed, but since that's getting bigger, this has to get smaller. Okay, so the speed has to decrease, right? The speed has to decrease. I should say, you know, this is some regular thing, and then this has to be less than that, okay, for momentum to be conserved. Okay, so I used to do particle physics. I already told you that. And so let's have some examples from particle physics. Okay, so Fermilab, when it was first built, all of the experiments were called fixed target, which just means what it says. Okay, so you have the protons being accelerated to nearly the speed of light, and then they would be extracted from the beam, and they'd go this way, and they would hit a fixed or stationary target. And then all sorts of cool things would happen, all right? So that's called fixed target. Later on, they learned how to do colliding beams. So let's say protons go this way. Well, you can get protons going this way, and then let's say antiprotons going this way. So you have the head-on collision, you know? But they didn't know how to do that for quite a while. So let's do a fixed target experiment. So here's an example of a fixed target experiment. So you have a stationary target proton. So just have obviously you don't just have one proton, right? You have like a thin film, thin metal film or something like that, which is, you know, gazillions of protons. But okay, so you have a stationary target proton, and you have an incoming moving proton from the Fermilab accelerator. Okay, and so this moving proton hits the stationary proton, and what happens? All sorts of different particles are created with different velocities and masses and you know what, directions and everything, okay? So that's particle physics, right? So before and after. And this is like in midair, you know? And we're just going to assume it's along the horizontal plane. And so we're going to say that momentum is conserved, all right? All right, so if momentum is conserved, that means that P initial has to equal P final. So the question is, what is P initial? Well, I mean the total, right? This is P initial total equals P final total. What's P initial total? Well, the stationary proton has no momentum because it's stationary. So P initial is just the mass of the proton times that initial speed. All right, so it's just the mass of the proton times the velocity of the proton, right? Initial. Okay, what's P final? Oh my gosh, come on! You have all these particles, right? So what you have to do is you have to add them all up, you know. So it's a vector sum, right? M initial, V final, vector, right? So you have to add up every single momentum vector for all of these things. Okay, that's what you have to do. You know, that's what you have to do. And so what you would do is you would say let's say that this is the x direction. So this would be, so if you want to do x, you have that, and you do that, right? Okay, let's do y. What's p initial y? Okay, remember saying that this is x, this is y. So p initial y is 0. So that means that the sum of the m, I, v, I, well, final, I guess. I guess I'll put an I here. That would also have to be 0, right? So that means that, all the momentum going this way has to cancel the momentum going that way. So that's how you do it, this momentum conservation. And, let's say your detector didn't detect a certain particle. Well, then you can infer what its momentum is just using conservation of momentum. We did that all the time. Okay, so again, that's fixed target. Then collider mode is like this, right? So you have some particles going this way, some particles going that way, and they collide head on, right? Some people call it annihilation, okay? Okay, so here. Okay, so a proton is made up of quarks, okay? Quarks. So quarks make up protons. 3 quarks, in fact. Don't worry about it. All right, so when you have these really, really high energy experiments, you're not only are you colliding protons, you're really colliding quarks. Okay, so this is one of these collision experiments, So I have a quark, let's say, colliding with an anti-quark. Now, what's it look like? I mean, what do you think you're going to, what's the initial momentum going to be, most likely? Around 0. So therefore, what's the final momentum going to be? Well, around 0, right? Okay, so this is, let's talk about a 2-jet experiment. What's a jet? Well, when you have a high-energy quark hitting a high-energy anti-quark, you can have a whole bunch of particles created, gobs and gobs. And so when they kind of come out as a unit, you call it a jet. Okay, so here's the data. Now there's really a lot of particles. You can't really see them all, but so this is after the collision. You see a bunch of particles going this way and a bunch of particles going that way. Now, if the initial momentum was 0, the final momentum is going to be 0, right? Well, doesn't that kind of look like the final momentum is going to be 0? Yeah, sure does. Okay, let's do a 3-jet experiment. Okay, now if you have 3 jets, what's going to be the angle? So these are basically back-to-back, right? You got to be back-to-back in order to cancel. This is not going to cancel with that, correct? No way. So this is back-to-back. Now, what if you have 3 jets? What is it going to look like? Well, like that, right? Where this angle equals that angle, what equals that angle. And so that's the data. So momentum conservation, it's true. It's a true principle. Okay, it's a true principle. Okay, let's do a decay. All right, so this is different than a collision. So a decay is when something dies, ceases to exist. So here you have something called a muon. Muons don't live very long. So you have a negative muon, and it doesn't live very long. So when it dies, or what we call in physics decays, what's formed is an electron. Don't worry about all the details. Anti-electron neutrino and a muon neutrino. Don't worry about it. Just 3 particles. That's the important thing. So this is supposed to be like a time-lapse, movie or something. So we have the muon moving. Then it kind of gets old and decrepit and it dies, right? And then you can see the electron and the 2 other particles. And so they move off like this, right? The electron keeps moving this way, and one neutrino kind of goes off this way, the other one goes off that way, okay? This is time, all right? Now, so all right, so momentum has to be conserved, right? Because it's, again, let's say it's along the horizontal plane. So let's call this the x direction and this the y direction, along the horizontal plane. Okay, so what's P initial x? Well, it's just the momentum of the muon, right? It's just the momentum of the muon, Okay? what's P initial y? Well, there is no P initial y, right? This is going in the x direction. There's no y direction. I mean, there's no y. So it's 0. Okay. What's P final x? So after the decay, what's P final x? Well, it's the momentum of the electron and also the x component of this guy, right? This guy and this guy. Just the x pieces, though. So it's a P electron plus P neutrino plus P antineutrino. Just the x components, right? Just the x components. Okay? And what has to be P final y? Well, that has to be 0, right? So that means that the y momentum of this guy has to cancel the y momentum of that guy. Okay? All right, so in other words, so this has to equal this, and that, of course, is equal to that. And that's how it works. Okay, and it works. Okay, in nature, it works. All right, momentum is really, really conserved, even on this tiny, tiny scale. Okay, here's kind of a nice question for you that we'll end on. Yeah. All right, 2 carts of identical inertial mass are put back to back on a track. Okay, back to back on a track. Cart A has a spring-loaded piston, so right, so it can do that, right? Cart B is entirely passive, so no spring, just sits there. When the piston is released, it pushes against cart B, and what happens? And you're supposed to ignore friction. So pause your video and figure it out, please. Whatever. Okay, so as soon as you see this ignore friction, what do you think of? Isolated system. If it's an isolated system, momentum is conserved. Okay, so all right, I'm supposed to put them back next to each other, sorry. All right, so 2 carts, identical mass, back to back. One has a spring, the other one doesn't. What's the initial momentum? 0. What has to be the final momentum? 0. They both have the same mass. So therefore, this one has to have velocity that way. That one has to have velocity that way. And the velocities have to be the same because P initial equals P final. Simple as that. So it's mv that way plus mv, I call it 1 and 2, okay? That way, right? So the velocity, these guys have to be equal and opposite to cancel. So the answer is both carts gain equal speed, opposite direction. All right, so let's just review impulse momentum, this long thing, momentum conservation. If you have the sum of the external forces along one particular plane, or maybe both, I don't know, whatever, you know, the change in momentum is 0, so the momentum is constant. That's the important part. And then we learned about this rebound bit, right? No rebound, there's the force. If you have a rebound, a perfect rebound, you get twice the force. Collisions, elastic, the definition of elastic, definition of inelastic. And we'll do that later. Thank you.